We are talking about partial and semi-partial correlation coefficients, and in the last videos, I focused on semi-partial correlation coefficients. It's time to turn our attention to partial correlation coefficients. Calling up my R notebook, on line 56, note I say, for the partial correlation of income with doctors after accounting for beds, we remove beds from both income and doctors, then correlate the residuals. Remember when we looked at the semi-partial, we removed the effects of beds from income, but we didn't remove it from doctors. And that gave us a semi-partial. For the partial correlation, we remove the effect of beds from both income and doctors. So notice how I do this. I regress income on beds. That is, I'm taking into account the effect of beds. What would the residual of that be? Everything else after beds has been removed. And then I look at beds predicting doctors. That is, I regress doctors on beds. What would the residual of that be? Everything else other than beds. So I've removed the variation of beds from income and the variation of beds from doctors. I call this partial model 1 and partial model 2. And what I do here on line 61 is I correlate the residual of partial model 1, that is, income after beds has been removed, with partial model 2, that is, doctors after beds has been removed. And what I get is how much correlation I have of income to doctors when beds have already been accounted for. So let's go ahead and see what that is. It's 0.45. That's the correlation or the partial correlation of income with doctors. Why partial? Because beds has been removed. We also have the partial coefficient of determination. That is the partial squared. The partial coefficient of determination, or partial squared, is about 0.20. What does that tell me? About 20% of the variation in physicians after beds has been removed can be accounted for by income after beds has been removed from income. Let's look at our Venn diagram again to see this as a picture. So remember, for semi-partial, we looked at this unique portion of x1 being correlated or associated with the variation in y. That unique portion is labeled as A. And we looked at that in a ratio with the total variation of y. That's what made it a semi-partial, because in a partial, you're going to remove x2 from both x1 and y. And so, clearing the picture here and trying again, here is the portion that remains of variation of y after x2 has been removed. I'm now looking at the variation of x1 with y after x2 has been removed. So note that the denominator here for a partial is only the a plus e sections, that is, after we've removed x2. Also note in the denominators that if you compare the denominator of a partial with the denominator of a semi-partial, note that the semi-partial denominator will always be at least as big. At least as big. The only reason it would be equal to the denominator in the partial if there was no b or c. So it will always be at least as big as the denominator of the partial. And when you have bigger denominators, what do you get? You get smaller numbers. So therefore, a semi-partial will always be, because it's going to have a bigger denominator, it's going to be less than or at most equal to a partial. So let's look at our other way of looking at this via residuals, the other kind of diagram I made for you before. Let's do that for partials. Here it is with semi-partials. Remember what we did is we regressed income on beds, that is, we predicted income from beds. But we also talked about, well, what else goes into income if it's not beds? A bunch of other stuff that we called the residual. That's E, the residual. And then we correlated that residual, that is everything other than beds, we correlated with physicians, and that was the semi-partial. So what we're going to do now is we're going to do the same thing in which we predict income from beds. Of course, there's a whole bunch of stuff we're not predicting with this, and we'll call that residual 2. Why 2? Because I'm also going to predict my response variable, which was doctors. I'm also going to predict that from beds. Now, there's a whole bunch of other things that also could go into the number of physicians in a small city other than hospital beds, and that's the residual here. And what is the partial correlation? It's the correlation among these residuals. That is, how much overlap there is, how much there is that is associated of the residual with doctors after taking out beds, the residual with income after taking out beds. That's the partial correlation. So if you think back to a semi-partial, we talked about how it could be abbreviated this way. With a partial, we would do it like this. Why? Why do we do it like that without the parentheses? Because here we're indicating that we're only taking the third variable out from variable 2. Here we're indicating we're taking variable 3 out from 1 and 2, or using the words to for a semi-partial correlation of doctors with income. I have doctors, I have income, and we're going to take beds out of both of those. Going back to our notebook now, you see what we did. We took beds out of income, beds out of doctors, and we got a partial correlation of 0.45 and a partial correlation squared of 0.20. So putting it all together with semi-partials, we're seeing how much of the total variation a variable can contribute to the model after removing the effect of the other variables in the model from that explanatory variable. I often learn a lot when I use extreme examples, so let me use an extreme example here to provide a better understanding of the difference of semi-partial and partials. Let's suppose that we have a variable y, and let's suppose we have a variable that is extremely highly correlated with y. In fact, let me do this. Let me move the y to out here. And we have this variable that's extremely correlated with y. It's like this. Okay, so it's accounting for, I didn't draw that very well. Let me try one more time. It's accounting for almost all the variation in y. So we'll call that x1. Now we come along with x2, and we want to know what is the partial and the semi-partial. Well, let's suppose that x2 actually explains everything else. let's suppose that x2 actually does explain. That's not everything else. Let's try it again. Yeah. Sorry about that. I accidentally was using the eraser. So here's y. Here's x1. And x1's explaining almost all of y, except we got that little sliver there. And let's say that x2 comes along here, and x2 explains the rest of this. Okay, let's make this little horizontal hashtags. It explains the rest. Well, the semi-partial is not going to be very big because there's not that much left to explain. And remember, the semi-partial is how much of the total variation of y you explain after accounting for the other variables. So the semi-partial is not going to be very big, but the partial correlation is going to be 1 because you're explaining everything that's remaining. So semi-partial is out of the total variation of y. Partial squared, semi-partial squared is total variation of y. Partial squared is out of what is left to explain how much of it can you explain.